happy to have Yacine Ali-Haimoud visiting from Johns Hopkins. He's going to talk about new frontiers in cosmology.
Okay, hi everybody. Thank you very much for the invitation. Sorry for the slight delay. Also, I thought that this was going to be a colloquium. I realized 2 days ago it was a seminar, so bear with me if it's not super smooth. So I will compress two topics, and then I will expand 2 topics I was going to talk about. All right. So in the last 2 decades or so, cosmology has transformed from an order of magnitude field to high precision, highly quantitative branch of physics. And these 2 observables are the pillars of modern cosmology: CMB anisotropies in temperature and polarization, and large-scale structure surveys. So both of these observables have huge challenges in terms of technical challenges, observational challenges, but there are also theoretical challenges in the sense that one has to really be able to predict very precisely what we are observing in order to analyze the data. So let's look at the CMB first. So the Planck Satellite is the culmination of a series of full-sky observations, and as you can see in this image, from Kobe to WR to Planck, Planck has really measured the CMB with an exquisite sensitivity. So this is the angular power spectrum of CMB temperature fluctuations from Planck. And what I want you to get from this picture is that the error bars here are extremely tiny. Okay? And so they're so tiny that, in fact, one had to be really careful that the theory, the errors on the theory were at least as small, if not significantly smaller, than the error bars from the instrument. Okay, so the theory, the bottom line is that the theory need to be accurate to the 0.1% level or so. And before Planck, so the theory that goes in predicting these acoustic wiggles here includes, first of all, essentially fluid equations expressed in the language of general relativity. And secondly, it includes the theory of recombination. So one needs to understand exactly this kind of innocent-looking curve, which is how the universe went from fully ionized at high redshift to almost fully neutral at redshift below 1,000 or so. Okay? So the idea is that this recombination history needed to be computed at the level of 0.1% accuracy. And not only did it need to be very accurate, it also needed to be computed and implemented in a fast way, because the way that we analyze CMB data is by running tens of thousands of theoretical models and comparing with the data in Markov chains. Okay? So lots of people worked on this, and this is kind of a teaser. If you want to learn more about this, I can tell you more about this. But the summary is that at the end of all this work, I wrote, in collaboration with Chris Serrata, this code, high-rec, which is publicly available. This code is really accurate. We included lots of different physics to make sure it's accurate at the required level for Planck. It's very fast, and this is mostly due to a factorization method that I introduced. I can tell you more about it if you're interested. Actually, I talked about this 5 years ago.
So the 0.1% is as accurate as electroweak physics. As in electroweak physics.
I don't know. No.
At CERN and SLAB. Yeah, the same.
Okay.
0.1%.
Okay. So this code is in excellent agreement with the similar code that was written independently by Jens Klub and collaborators, which is called Cosmology. We compared them. They're both included in Boltzmann codes for the CMB calculations. And the bottom line, the main message here is that without these detailed recombination calculations, the cosmological parameters that we extracted from Planck data analysis would have been biased at the level of 2 to 3 standard deviations. So it would have been a little bit lame to have a $1 billion experiment and not get the right cosmology because we didn't get recombination right.
Just to make sure I understand, so this was included in the analysis by Planck?
So this was included in a strange way by Planck in the sense that they fitted, that they have an old code and they fitted for fudge functions of the old code using my code and Jens's code. But so it was included in an indirect way for reasons that are beyond my personal understanding. So that was just a quick overview of one of the theoretical challenges for CMB anisotropies.
So these errors on that you put there, so how much do they contribute to the final?
These errors?
Yes.
Oh, I mean, this is way sub 1 sigma. Right. And this is just an estimated error. So there are a bunch of effects that we tested, and there were 10 to minus 5 corrections, or a few times 10 to minus 4 corrections, and we said, okay, this is negligible enough. Because otherwise you end up having too big of a code. can't include every possible physical effect. So this was the first pillar. The second pillar of modern cosmology is large-scale structure. So the theoretical challenge here is the nonlinear regime. And at least a couple of people here are working on the general problem of clustering of cold dark matter, baryons, and how galaxies trace the cold dark matter in the nonlinear regime. And this is still an open problem, I would say. A perhaps more specific problem is how massive neutrinos affect the formation of large-scale structure in the nonlinear regime. And so the idea is that we know that neutrinos have a mass. We know this from flavor oscillations. And in order to measure, or at least set upper limits on the neutrino mass, we need to understand exactly how they affect large-scale structure, in particular in the nonlinear regime. Because, for example, Lyman alpha measures, first of all, nonlinear objects, the Lyman alpha absorbers, and also probes their distribution on nonlinear scales. So the standard way to account for massive neutrinos in the nonlinear regime was to put them in n-body simulations and simulate them as particles, just like you would do with cold dark matter. So for instance, I'm showing here the results of Rossi et al. And so this here is, you recognize a cold dark matter snapshot, so you can see halos, etc. You see that the density varies over 3 orders of magnitudes. In contrast, the neutrino component here is extremely smooth. So even though they show this whole range, really it varies over something like 0.1 or 0.2 orders of magnitude. Okay? So what you can see here first is some real structure. So you see that the halos in the cold dark matter lead to halos, even though they're much smoother, in the neutrino component. This one also is a halo. But I don't know if you can see here, but all the kind of graininess that you should be able to see is really artificial. It's shot noise. It's the result of the fact that we're using a finite number of particles to simulate an almost smooth component. So Simeon Bird and I came up with an efficient and I think elegant way to implement what massive neutrinos do in structure formation simulations. So we do use the full power of numerical solvers to follow the cold dark matter and the gas with hydrodynamics, for example. But for neutrinos, you can solve analytically for their clustering as a linear response to the gravitational potential. So you can find a linear response to the nonlinear gravitational potential. Okay? And I can tell you again a little more about this if you're interested. And so the bottom line is that we evolve simultaneously and self-consistently neutrinos and cold dark matter, accounting for their mutual gravitational interactions. But we replaced all the neutrino particles by just a simple one-line equation. And it's very accurate for the matter power spectrum. The accuracy, when compared to the particle method, is way below the percent level. So the bottom line is that we replace something like 100 million to 10 billion to a billion particles, neutrino particles, by a simple equation. There's no shot noise issue, and there are other issues that I didn't talk about that this does not suffer from. So the main advantage here is that you can save a lot of memory and CPU time, and you can use this to really simulate the actual complicated physics, which is the cold dark matter and the baryons. And we made a patch for the n-body code gadget, which is publicly available. And finally, it works very well for the matter power spectrum, but there are more subtle effects that may require a slightly improved treatment, so that's something we're working on to treat the slowest neutrinos as particles, so have some kind of hybrid method. So these were kind of the teaser 2 topics. Again, I'm happy to talk more about them if you like. So let me move on to the main topics of this talk. So in the post-Planck era, there's still very important questions that remain unanswered. And for instance, the nature of dark matter, okay, which we still don't know what the dark matter is. We still don't know exactly how dark is the dark matter. So one of the big questions would be how strong are the weak interactions of the dark matter with standard model particles. Another very important question is that of the initial conditions. We have some measurements from Planck on the power law of the primordial power spectrum, but we only have upper limits on, for example, the primordial universality, or we have very little knowledge of the very small scale primordial power spectrum. And in order to really constrain the physics of inflation, it's important to measure the properties of initial conditions better. So it's important to explore other cosmological probes, either futuristic cosmological probes. So in this little time arrow, I briefly mentioned these 2 topics. In the remainder of the talk, I will talk a little more about the CMB spectrum and how spectral distortions can set limits or can help us probe the early universe, and in particular energy injection in the early universe. And I will show you in particular how we can use the CMB spectrum kind of like a direct detection experiment, and we can probe interactions of the dark matter with standard model particles. And in the second part of the talk, I will tell you about 21 centimeter fluctuations from high redshift, which is, at least from today, considered as a futuristic probe. But eventually, this will become the ultimate cosmological probe, and in particular, could help us set really good measurement on the initial conditions. All right, so let's start with dark matter interactions, if you forgive me. Any questions so far? No. All right, so as you all know, I'm sure, the CMB has the spectrum of a black body. It's the best black body that we know. Well, the limitation on how black it is depended on how black the test black body that was compared to was. So it's a black body within about 50 parts in a million. This earned the Kobe-Fires team half of the Nobel Prize in 2006. So on this figure here, the error bars are smaller than the line width. The former Fires team, led by Al Kogut, are thinking of a new experiment, Foucault's Bixie, which should have a sensitivity of 3 orders of magnitude or more than Fires. And so it's, I think, interesting to start thinking again about what one can learn from spectral distortion of the CMB. So first thing I want to tell you is that the CMB cannot possibly be a perfect black body. Okay, there are distortions that must be there, at least if we understand very basic physics correctly. So for instance, the recombination process itself, so here I'm just drawing schematically the energy levels of hydrogen. As hydrogen recombined, radiatively mostly, it emitted photons, and a few photons per hydrogen atom. And knowing that we have something like 10 to the minus 10 baryons per photons, this led to a distortion of order 10 to the minus 9 to 10 to the minus 8 relative to the CMB. And this distortion has features, so these bumps and wiggles that you see correspond to line transitions, to bound-bound transitions or free-bound transitions in hydrogen. And they are broad because the emission took place over a broad range of redshifts. So this is very small, it's parts in a billion or a few parts in a billion or so. So it might not even be at the range of Bixie. But this could become, in the future, some new cosmological probe. Okay? And so in particular, a way to probe cosmological parameters in a different way than the CMB. For instance, if you vary the helium mass fraction, or the helium fraction, the primordial helium abundance, this would have a direct impact on the spectrum because you would have different relative amplitude of hydrogen versus helium lines.
That's a big variation in helium.
Yeah, this is just a visual illustration, of course. Yeah, this is just a visual illustration.
Nice about this 10 to minus 8. So what sets this number? Is there some fundamental limitation on how well one can do?
My understanding is that the way they measure it is that they compare with a black body, something that's made, and it's like a cone, some kind of a cone, and they figured out that just by making the cone a little smoother, it would be a better black body. That's my rough understanding of how it works.
So if I'm thinking futuristically at the same time scale as for 21 centimeter, so what would be the ultimate sensitivity which one can achieve?
I don't know if there's a fundamental limit to how sensitive you can get. Yeah, I don't know. What sets this number 10 might say, I'm not sure. Okay. How smooth you can get the black body, I'm not sure. You have to control the temperature gradients, reflections, and I don't know. So anyway, in general,
what would be the time scale for Bixie?
So Bixie is at the stage of being proposed, and they already have. I saw in Chicago. So it's a Fourier transform spectrometer. So they already have some smaller models, prototypes. But I don't know exactly what the time scale. It will depend if they get funded or not. But it should be, if it does happen within the next, a decade or so, something like that.
So is the one that you showed the biggest spectral distortion?
No. Well, I mean, expected spectral distortions. I will get back to this in a minute. But
so it makes sense to make some.
From early universe physics, the kind of standard expected in the vanilla universe are of order 10 minus 9 or so. So it's not the biggest, but it's of the same order as all the other ones that I will mention before. And then you may have additional spectral distortions from non-standard physics.
Okay. So Bixie will
So-
see something only if
Yeah.
it's not standard physics, right? So it's kind of
Bixie will see some foregrounds, for
Ah,
sure,
okay.
which may also have some interesting physics. So in general, so this was the recombination lines, but in general, distortions of the CMB tell us about the thermal history of the universe at high redshift. So if you inject heat into the photon-bearing plasma at redshifts greater than about 2 million, this heat gets fully thermalized, so you end up with a black body with a different temperature, and that's not observable as a spectral distortion. If you inject heat at later times, and if this heat is injected at redshift greater than about 300,000 or so, then it gets partially thermalized, so the photons can efficiently change their energy, but because you can no longer produce and destroy photons efficiently, you end up with a Bose-Einstein distribution with a chemical potential, so-called mu-type distortion. At redshifts below about 10,000 or so, there's no thermalization, and so you end up with a Sunyaev-Zeldovich type distortion, the Y-type distortion. And finally, in between, the shape transitions kind of continuously from one to the other. Just to illustrate how these shapes look like, this is from a paper by Jens Kluba. So the red line is just a temperature shift. And as you decrease the redshift of energy injection, it transitions to this blue curve and then to this white curve. So the main message here of this plot is that the shape of this distortion is really like a chronometer telling us about when the energy was injected. And the amplitude of the distortion is proportional to the fractional energy injected in the CMB. And this is what I will use in a few minutes for limits on the dark matter. So as a note, someone asked a question, so the Y distortion has a large foreground from the Compton scattering in the intergalactic medium, and this is something like about 10⁻⁶ or so. And so what I will use later on is that I can only set limits on primordial distortion, primordial energy injection, if it happened at redshifts greater than 10 to the 4. Because later than that, it will cause a Y distortion which has a big foreground. Of course, future analysis will take care of this in a more rigorous way. So, several processes that can generate spectral distortions. So the first three are processes that happen in the standard universe. Dissipation of acoustic waves. Adiabatic cooling of baryons, which is very similar to the effect I will get to. So you will understand what this means. I mean by this. Sunyaev-Zeldovich effect at low redshift. The rest are processes which, and so these are of the order in the standard universe. If you extrapolate the very small scale power spectrum to very small scales, this is 10⁻⁹ or so, and same for this. The rest are processes that may or may not happen, but can, so the spectral distortions can be used, for example, to set limits on primordial magnetic fields, on annihilating or decaying dark matter. This was worked out in many different papers. What I will tell you about now is how dark matter scattering, and I emphasize that it's scattering because we got cited like a few times and are always wrong. So it's not annihilating dark matter, it's how dark matter elastically scattering with center model particles can also distort the CMB. So as a small introduction, we do have some limits, of course, several different observables, but perhaps the most famous and intuitive is direct detection limits on dark matter nucleon interactions. So first thing to know is that these rely on assumptions about the local, at Earth, dark matter density and velocity distribution. And as you will see, the probe that I will show you does not have such assumption. And the second thing is that these are mostly sensitive to masses greater than a GeV or so, because for lower masses, the dark matter is not heavy enough to impart sufficient recoil to the target nuclei. And you will see that with spectral distortions, we can actually target lower masses. So how does dark matter, if it scatters of center model particle, how does it distort the CMB? So if the photons cool down adiabatically on their own, their temperature goes as 1 over the scale factor, 1 plus z. Now if you take a non-relativistic dark matter particle, it would cool down faster if it was left alone. Its temperature or its velocity variance would go as 1 over a squared, or 1 plus z squared. Now if you imagine that the dark matter scatters off photons, there will be momentum exchange, but also heat exchange between these two components. So there will be a net heat flow from the photons to the dark matter, which tends to cool down faster. So this, you can figure out that this leads to a slightly faster rate of cooling down for the CMB. So the temperature of the CMB, or rather the mean energy of the CMB, would go as 1 plus z to the 1 plus epsilon. And this epsilon, you can show that it's the ratio of the number density of dark matter particles to the number density of photons.
what does it depend on the nature of the dark matter particles? I mean, what do you assume?
I'll get
Is it
this.
very generic? Or?
Yeah. So far, it's only if you have. So far, it's very generic. If, as long as the dark matter and the photons are in thermal contact, then this will happen, and then I will explain a little more. So if the dark matter scatters not with photons, but whether with electrons, the same process happens, but indirectly. So the reason is that the electrons are themselves very tightly thermally coupled to the photons through Thomson scattering, and this is true all the way to redshift about 200 or so. So you will have an indirect heat exchange from the photons to the dark matter. Same thing if the dark matter scatters with nuclei, because the nuclei are themselves Coulomb scattering with the electrons, and so they're very tightly coupled to the electrons, which themselves are coupled to the photons. Okay? So the bottom line is that the energy extracted from the CMB is this epsilon, the ratio of the number density of dark matter particles from photons, there's some numerical factor for the unity in front, times the log of some maximum redshift to a minimum redshift. This epsilon is, so this number density, we don't know the number density of dark matter particles, we know the mass density. So this is inversely proportional to the mass of the dark matter particle, which is why this effect is more important for light dark matter particles. The maximum redshift is about 2 million, because as I explained before, anything that happens before redshift of 2 million gets thermalized and we don't get a distortion. And the minimum redshift is corresponds to the time at which this thermal coupling becomes inefficient, the time at which the heat flow ceases between the dark matter and the photons. And so this depends on the cross-section and on the mass of the dark matter. So specifically, we considered cross-sections which are power laws, so dark matter photon cross-section, which is some power law of the energy of the photon. And just to give you examples, so I'm not a particle physicist myself, but I will just give you some examples. You have millicharge, or dipole, this gives you a constant cross-section, dipole dark matter, quadratic, Rayleigh dark matter. Neil Weiner has a paper on this, gives you a quartic cross-section. For the dark matter, baryon scattering also took power law dependence on the relative velocity, and again, for example, for n equals plus or minus 2, this would be an electric dipole dark matter. So this here I'm plotting, for instance, assuming a constant dark matter proton cross-section, which is shown here in the x-axis, and this is the fractional distortion of the CMB, so the fractional energy extracted from the CMB, which translates to a distortion. So first thing to notice is that the lightest the dark matter particle is, the larger is this asymptote here. The second thing here is that there's some plateau here, and this comes from the effect of baryon. So you replace all what I said, you replace the dark matter by the electrons, and the same effect happens. The electrons take away a little bit of heat from the photons, and the fractional distortion is a few times the ratio of number density of electrons to photons, which is a few times 10 minus 10, and it works out to be a few times 10 minus 9. The kink here is once the cross-section is large enough that the dark matter thermally decouples at redshift 2 million. And finally, this plateau is when the dark matter couples all the way to redshift 10 to the 4. So from saying that Phi-RAS observes no more than this, and Bixie will observe no more than this distortion, you can cut through here and set a maximum cross-section on the interaction with the dark matter. So which is shown here. So here we could set new constraints on the dark matter interactions from 20-year-old data, copy Phi-RAS, assuming that the distortion is no more than 50 parts in a million or so. So first thing to
sorry, can you stop and explain this plot?
Sure. This one or the one before?
This one.
So you understand this one? You're good with this one?
Right. I think so.
Yeah. So yeah, I'm just saying that the larger the cross section, the more the dark matter interacts, and the more it can extract heat from the CMB.
Mm-hmm.
And so
just for the lighter ones, you have more of them. So
and the lighter you have more of them,
so
they
that's
can
why it's
extract.
higher.
Right.
So
And then if you say I observe no more than some amount of distortion, so say this would tell me for a mass of 3 MeV, this would tell me that the cross section can be no larger than 10 minus 26. So that's how this plot translates to this
Okay,
one.
but this spot is only for Kobe and Phi-RAS.
Right. Yeah, because I guess I didn't. So I should have plotted. So if you go to even smaller masses, then you would go beyond this
Right,
limit.
yeah. But if you go to the next one, sorry.
Yeah.
What are the? I'm just lost as to the allowed the allowed regions are which
Oh,
and the disallowed regions
sorry, yeah. This is the maximum cross section. So above the line is disallowed.
are. Okay.
It's an upper limit on the
Got it.
cross section.
Okay.
And so for comparison, these are upper limits from direct detection experiments. So this is from the CREST collaboration, and this is by Essig et al. Using the Xenon 10 detection, the Xenon 10 experiment. Sorry?
Why do they all turn up at F1?
Sorry, say it again?
Why is there a
Yeah, why is there a vertical asymptote? Because from the previous plot, if the dark matter is heavy enough, it will never reach the phi-s amount. So if the dark matter is so heavy that even if it's always in thermal equilibrium, then because it's not abundant enough, it will never extract enough heat from the CMB. Okay, because the amount of heat extracted is proportional to the number density of dark matter particles.
In the mass range variable limit, there's also constraints from ineffective, right?
Yes,
the
so that's something I
PBM
want. Yeah, that's a very good point. I want to look in more detail. So there are constraints. Yes. So from the CMB, I think you can avoid these
Yeah,
constraints.
for BBN.
But from BBN, and I think the limits are of order and effective is
About one thing.
about 1. So I think you can sort of evade them. But something I want to look in more detail. Yeah.
Sorry, in the limit of very large cross section, when it's always in thermal equilibrium, then there are no distortions, right? Then it's all thermal, so it just takes.
No. So the dark matter. So sorry, another thermal. So if the dark matter is always in thermal equilibrium, just like the baryons are always in thermal equilibrium up to redshift 200, it means that the dark matter has a temperature that's always very close to the photons, but there's this tension between the two. The photons have to constantly heat up the dark matter to maintain it at this temperature. So even though they're very close, there's still a heat flux from one to the other. So then you do get a distortion.
So this heat flux not only changes the temperature, but also.
Yeah, sorry. So I guess maybe it's slightly misleading when I showed here. So this should really be the typical. It's a heuristic.
So it really changes it.
It's really the characteristic energy of CMB.
But I think this is
Not the
constrained by ineffective during CMB too. Because
I don't think so
because when the dark matter freezes out, you're going to heat the photons relative to the neutrinos.
But the ineffective constraints from the CMB come mostly from redshift less than 10 to the 5 or so. It's really the Hubble rate,
But
right,
you're-
redshift 10 to the 5 or less, corresponding to scales which are sub-horizon, CMB scales sub-horizon.
But if you change the relative photon neutrino temperature after the neutrinos decouple, then the CMB.
Let's talk about it. I would like to think more about this, yeah, because I think there's.
What is meant by Rayleigh dark matter?
So
What does it mean?
I don't know if Neil will, when he sees the video, can answer that. So Rayleigh dark matter, I don't know exactly the details of the model, but basically, just like Rayleigh scattering for atoms, if you're at very low frequencies and you have a resonant line, then the frequency dependence goes as frequency to the fourth, just like Rayleigh scattering in the sky. So anyway, it's going to be tough. To get out of this is that first of all, okay, these direct detection limits may seem are much lower in amplitude. However, they are in the mass range, which is completely disconnected like the ones. So with spectral distortions, you can probe a different mass range than direct detection limits. Okay, and if you had instead of fire-s, you have Bixie, you could extend this wall to a larger masses. So you could set limits on the dark matter proton electron photon interactions to much larger limits. I also want to emphasize that there's no direct detection limit on photons, dark matter photon scattering. 1, and 2, again, that this is a rather, of course these results are not corrected in factors of 2, okay, because it's kind of a simple derivation, but it's much more robust, I think, than the assumptions needed from knowing the velocity dispersion distribution of dark matter for direct detection experiments. It's simpler, cleaner physics. So this is mostly to answer a question that Neil asked me, so it's for the video. So in preparation, I want to apply this for specific dark matter models. And so Neil asked me, so for Rayleigh dark matter, if the energy goes as e to the 4th, so the cross-section dimensionally would be e to the 4th over some characteristic energy scale to the 6th power. And so the limit I got translates to something that's not so good. The scale has to be greater than 5 MeV. So for that specific model, it's not an incredible limit. That's kind of a parenthesis. So the bottom line of this part is that spectral distortions provide a window in the thermal history of the universe at times greater than 2 months after the Big Bang. So one of the things you can probe is, for example, the fundamental properties of dark matter, whether it annihilates, decays, or scatters with standard model particles. And they have not been measured since the Kobe fire acid. And so there are proposed experiments that will measure them with a precision of 1,000 or so. So I think it's timely to explore this in more depth. So let's move to part 2. I'll take any questions you have. Part 1. Okay. So 21 centimeter fluctuations. The very basic idea. So once hydrogen has recombined, after recombination, neutral hydrogen in its ground state is split, okay, with 2 hyperfine states, depending on the, classically speaking, the alignment or anti-alignment of the spins of the electrons and protons. The difference of these 2 energy states is 6 microelectron volts, corresponding to 21 centimeter for wavelengths. And then the idea is that you use the CMB as a background source, and these little cute clouds represent the early universe neutral hydrogen, and so you can then observe at the redshifted 21 centimeter frequency either an emission or absorption and map the universe at very high redshift. So this will open a new time frontier, okay, between the surface of last scattering of the CMB and modern day galaxy surveys. So at redshift less than 30 or so, so this is just showing the brightness temperature either in absorption or in emission and different epochs. So redshift less than 30 or so, you can probe the physics of the first stars and galaxy formation and reionization. At higher redshift, which is harder to observe, you can probe a much cleaner universe before the first stars are formed. And so this would be a very clean cosmological probe. It will be an extremely challenging observation. So you have foregrounds, galactic foregrounds that raise very steeply at low frequencies. The ionosphere of the Earth becomes opaque. So we may have to put telescopes on the moon, and specifically on the far side of the moon, because the Earth also has all this radiation emission. But I am a theorist, and this could become really the ultimate cosmological probe, and it doesn't hurt to start thinking about the underlying theory. So it will also open up a new scale frontier, and this is why it could be such a great probe. So CMB anisotropies are limited on small scales by the Silk diffusion scale, which corresponds to a wave number of 0.1 to 0.2 inverse megaparsecs. The large-scale structure surveys are limited fundamentally by our knowledge of the clustering on nonlinear scales, our ability to model these nonlinear scales. And even at high redshifts with the Lyman alpha forest, this corresponds to wave number less than a few inverse megaparsecs or so. In contrast, 21 centimeter fluctuations are in principle limited only by the gene scale, which corresponds to a wave number of about 300 inverse megaparsecs. And in addition, as opposed to CMB anisotropies, which are a 2-dimensional surface, this would provide you a 3-dimensional mapping of the universe. So the number of independent modes would go as the maximum wave number cubed. So you would have, in principle, a huge number of independent modes. So this has a huge potential. The Lopez-Aldariaga paper is one of the first to expose some of the things you could measure, such as warm dark matter, massive neutrinos, test of inflations through the measurement of the very small scale power spectrum, primordial non-Gaussianities, etc. You could also measure dark matter-barrier interactions. This was a paper with a student, Julian Munoz and Eli Kovets. I can tell you more about this if you're interested. So what's interesting for theorists, I think, is that the 21 centimeter signal is not, is simple enough that you can use perturbation theory tools, but it's actually not quite as simple as the CMB in the sense that nonlinearities at redshift 50 or 100 are already significant. And so in some cases, these nonlinearities mean that one has to be really careful. So for example, with Julian Munoz, a student, we worked out that intrinsic nonlinearities can be a huge contaminant to primordial non-Gaussianity searches, which would be one of the biggest goals, perhaps, of high redshift 21 centimeter surveys. But with the careful study, we showed that you could bypass this contamination if you essentially marginalize over some coefficients. In some cases, these nonlinearities actually help you.
So are you talking about nonlinearities in the gravitational growth, or are you talking about nonlinearities in the signal?
I'm talking about nonlinearities in the gravitational growth, and 2, the fact that the 21 centimeter brightness temperature is a nonlinear tracer of the density field, and I will illustrate this, how this works just in the next slides.
Okay.
So yeah, so in some cases this nonlinearity, the second type, and I will get back to this, actually helps in the sense that it can bring some signal at unexpected scales. Okay, so and this was a paper I wrote a couple of years ago with Don Meerberg and a student at Princeton, and so let me explain a little bit how this works, because I think it's kind of neat. So let me first go through a little bit of the basics of 21 centimeter. So the spin temperature is defined such that the ratio of the triplet state to the singlet state of the hyperfine split ground state of hydrogen is given by this Boltzmann formula. Okay? So the spin temperature is lies between the gas temperature and the CMB temperature. And these two are separate enough at redshift less than 200 or so once they fall out of equilibrium. On the one hand, collisions tend to bring the spin temperature in equilibrium with the gas. And on the other hand, radiative transitions, so absorption of CMB photons and stimulated emissions by CMB photons, tend to push the spin temperature towards the CMB temperature. So the bottom line is that you can figure out, it's a rather simple formula, but I'm not going to write it all, that the spin temperature is some function of the local gas density and temperature, this is because of these collisions, and of the CMB temperature. And this function is just some nonlinear function of everything here. Second quantity is the brightness temperature. So the idea, as I said, is that you have the CMB as a background source, and then you have some absorbers with the characteristic spin temperature and optical depth, and then you observe the outgoing intensity, or you can translate it to an outgoing brightness temperature. In the limit of small optical depth and in the Rayleigh-Jeans limit, the brightness temperature, which is the observable, is just the optical depth times spin temperature minus CMB temperature. And finally, the optical depth is usual definition, integral of the absorber density times cross-section times the line of sight. The absorbers is really the number density of absorbers minus the number density of stimulated emitters. And so this is proportional to the number density of hydrogen divided by the spin temperature. And finally, the length scale over which photons interact with the line in an expanding universe is inversely proportional to the local velocity gradient, which is Hubble rate plus gradient of peculiar velocities. So anyway, I don't mean to bore you, but the bottom line of all that, these few slides, was just to illustrate that the 21 centimeter brightness temperature, which is the observable, is a fundamentally nonlinear function of the underlying gas density, velocity gradient, and temperature. Okay? And the gas temperature itself is a nonlinear function of the density. So for example, if the gas cools down adiabatically, T would go at n to the 2/3, but the gas does not quite cool down adiabatically, so you have to also account for this. Okay, so now if I expand the brightness temperature fluctuations to quadratic order in the underlying density, what I just said before, that is fundamentally a nonlinear function, is just saying that these two coefficients are of order, of comparable order. Okay. Now you may think, okay, delta, I'm talking about the dark ages, there's no nonlinear structure, so delta square is small compared to delta. I can neglect the second term. However, the density field, the amplitude of the fluctuations depend on scale. So if I decompose this into large scale and small scales, and I will get back to what I mean precisely by large scales and small scales, you know that, so both are much smaller than unity, but the large scale fluctuations are always smaller than the small scale fluctuations. And secondly, this ratio, it turns out that during the dark ages, in fact, the square of the small scale powers, the square of the small scale fluctuation is comparable to the linear density fluctuation. Okay? It's just a kind of a numerical coincidence. This is illustrated here. So I'm showing here in red is the variance of baryon density fluctuation per logarithmic scale. So it's the k cubed p of k. And in blue is the square root of this quantity. So this is delta of order delta square, and this is of order delta. So what I was saying is that on these small scales here, this red line is of the same order or larger than the blue line on these large scales. Okay? And it just happens, around redshift less than 100 or so. All right.
The turnover there is just
This here,
Or what is the turnover there?
this is the gene scale. So this is
Okay.
the pressure of the baryons.
Okay.
And so yeah, this is what I was saying. This would set kind of the fundamental limit of the number of modes, because then you have an exponential suppression.
I see.
All right, so I'm going to go through a little interlude on the relative velocity effect to explain, how this affects the 21 centimeter signal. So this is based on a paper by Sadako and Hirata. So the idea is that before recombination, baryons are tightly coupled to the photons, so they undergo acoustic oscillations. In the meantime, the cold dark matter perturbations grow under their own gravity, oblivious to whatever the baryons are doing. And after recombination, on scales less than the newly much smaller gene scale, the baryons become cold essentially, so they start growing with the cold dark matter, and they start catching up with the cold dark matter. However, the main point of this is that up to recombination, in particular at recombination, they have very, very different initial conditions, baryons and cold dark matter, and in particular, they have very different velocity fields. And in particular, there is a relative velocity field between the baryons and the cold dark matter. And this is how the power spectrum of these relative velocity fields look like. So the variance of the RMS fluctuation in relative velocity is about 30 kilometers per second. And it fluctuates mostly on scales of about k of 0.01 to 0.3 inverse megaparsecs. And because it goes down very quickly here, it's homogeneous on scales of a few megaparsecs. Okay? So what does this relative velocity do? Okay, so now we have here a single Fourier mode. Black is the dark matter and blue is the baryons. Without relative velocity, they start in phase and they will remain in phase. And so they will grow together in harmony and get bigger, both of them get bigger under their mutual gravitational interaction. Now what happens if you have a relative velocity? So the dark matter, let's go to the frame of the baryons. The dark matter will be advected with respect to the baryons. So if the wavelength of the perturbation is smaller than the characteristic scale over which the dark matter gets advected with respect to the baryons, as I show in this very fancy animation, then from the point of view of the dark matter, it sees a time-changing baryon potential, which averages out over time, and the same thing happens for the baryons. So they will grow in time under their own gravity. They will not collaborate to grow under the mutual gravitational growth. So this will slow down the growth of perturbations on scales which are smaller than the characteristic scale that can be advected by this relative velocity. So in Fourier space, this corresponds to wave numbers larger than about 40 inverse megaparsecs or so. Okay? And this scale is actually much smaller than the scale on which the relative velocity fluctuates. So you can imagine the universe made of lots of different patches where the relative velocity takes on a fixed value, and on this little patch, the small scale power spectrum will be changed. So this is just to illustrate numerically. So we essentially followed the Tsiolakowicz and Hirata calculation, but we added a little bit complication. So we added, for example, the fluctuations in the ionization fraction. So this is showing the evolution of a mode with wave number 200 inverse megaparsecs. The dashed line is without relative velocity. The solid line is with a relative velocity of characteristic value of 1 standard deviation. So this is kind of confusing because it starts at -4, but basically you can see that the change is several tens of percent. So in places where the relative velocity is large, you can get several tens of percent of suppression, almost order unity suppression of the baryon fluctuation.
Sorry, and I'm trying to remember your power spectrum of fluctuations in VBC. That power was between 1 and 100 megaparsecs?
Yeah, it's typically on 100 megaparsec scales.
Okay.
It's like on the BA
So those
scale.
are the patches you'd be talking about. Okay.
Right, so this is the kind of the picture here.
Okay.
So the relative velocity fluctuates on like 100 megaparsec scales, and what happens for the very small scale power spectrum, and those scales, these wavelengths are very separated, but I can't show them very separated, but so you have to think about these are like 10 kiloparsec wavelengths or so. So on places where the relative velocity is close to 0, you have the standard small scale power spectrum, and on places where the relative velocity is large, you have a suppression of order several tens of percent, almost unity. Okay, does it make sense?
Mm-hmm.
And so now if I take the square of the small scale power spectrum, what you get is that this square fluctuates on large scales. So delta short squared fluctuates on long wavelengths, and it would not fluctuate. Well, it would fluctuate by order delta long, just due to the standard nonlinear growth. But so this makes it fluctuate by order unit. This effect. So what consequences does it have on the 21 centimeter fluctuations? So on small scales, you will get a suppression of the signal. This is the sort of obvious consequence of this suppression on small scales. On large scales, the less obvious consequence is the enhancement. So again, I wrote before, this fluctuation of the brightest temperature in 21 centimeter was this linear and quadratic term. And so if I ask what are the large-scale fluctuations of this guy, they correspond to the large-scale fluctuations of the linear guy, and the large-scale fluctuations of the square of the density field, which are dominated by the large-scale fluctuations of the small-scale power spectrum. Okay? And again, this guy is a Fourier delta short squared, which itself, as I argued before, is a Fourier delta long. So formally, at least, you expect that these two terms are of the same order. So what's important is that this enhancement here is proportional to the underlying very small scale power spectrum. So it's a large scale fluctuation that depends on the power spectrum on wave numbers of 100 inverse megaparsecs or so, which are very difficult to access directly. So this is the result, assuming that the power spectrum, the slope of the power spectrum as measured by Planck, can be extrapolated all the way to wave numbers of 1,000 inverse megaparsecs, where we actually have no measurement of the very small scale power spectrum. So the dashed lines are the standard 21 centimeter power spectrum, and the solid lines are these enhancements at redshift 30 and 120 due to these long, large-scale fluctuations of the small-scale power spectrum. Okay, so you can see that it's not quite order unity, but it's order, depending on scale, it's order a few percent to tens of percent. What I want to really emphasize is that this plot was assuming something about the very small-scale power spectrum, which we don't know. So now, in general, this effect will give you additional large-scale fluctuations which depend on the very small-scale power. And the reason that's interesting is that, so I'm sorry that this is very small, but it's not my paper. So here is showing the angular fluctuations of the 21 centimeter signal at redshift 50 by Lewis and Challoner. So the wave number of, the gene scale here corresponds to L of 10 to the 6 or so. So to give you an idea, if you were to try and measure directly the very small scale power spectrum with a very refined angular resolution, to reach these scales corresponding to wave numbers of 100 inverse megaparsecs, you would really have to have an interferometer of the diameter of the moon. Okay, so that would be a little difficult. So this effect basically brings back the signal, the underlying power spectrum from here, to fluctuations on large scales, which are presumably more readily accessible. So future work would be to really quantify this in detail for different models of the very small scale power spectrum. So there's and more generally about 21 centimeter, there's sort of a two.
This is going to fit on one slide.
Yeah. if you summarize things enough. So first thing, which I've been mostly interested in, is an exhaustive study of the theoretical prospects. What can we learn from 21 centimeter? For example, dark matter baryon scattering, for example, primordial non-negocialities, or the very small scale power spectrum. And one thing to have in mind is that if we're really going to measure so many modes and have such a very high signal to noise, the accuracy requirement will be much more stringent than for the CMB. So we really have to, yes?
The foregrounds would be problematic.
Yes. So that's my second summarizing, probably what will be the hardest part of the work, is how to model the foregrounds and how to get rid of the foregrounds, which are really humongous at these frequencies.
So what's the current state of some of these 21 centimeter telescopes, like such as Paper and others? If we were to summarize it.
I think there's no detection yet.
Yeah, so
right?
besides no detection, but
right.
Are they reaching sensitivity that they hoped? Are the foregrounds especially challenging more than they thought? So what's the status of that?
Right. I think they're reaching sensitivity that they hope, and they're still, I think, coming up with methods to subtract the foreground. So you have this technique of the wedge. I don't know if you've heard of it. So in Fourier space, you have the modes along the line of sight and perpendicular line of sight, and you have issues because of the beam of the telescope. But I think it's still in process to figure out really robust methods to extract the foregrounds. That's my impression so far.
When is it expected that telescopes will be installed in the moon? What is the time?
That I'm not sure. I mean,
Okay.
there are some there's something called DARE and there's something called Lunar. There are some projects, but I don't think it's not for tomorrow. But I don't know exactly the time scale. So yeah, so there's still a long road ahead, but eventually it will be the ultimate cosmological. So that's not something I would focus 100% of my time on, but I think it's interesting to think about it and see what can be learned from it. So as a summary, after Planck, it's important to start thinking about other probes. So I've worked on some CMB stuff and large-scale structure stuff, but I'm also interested in figuring out what we can learn from other future cosmological probes. One of them, which I think is the not so distant future, is spectral distortions. And there are serious experiments and serious people that are planning to build these experiments, which would get a sensitivity which is 3 orders of magnitude better than phi-rs. And so it's time to think about what we can learn from these experiments. And the sort of more future/futuristic is 21 centimeter high redshift fluctuations, which could become possibly the ultimate cosmological probe. So that's it. Okay, question.
More questions?
Question. With the spectral distortion limits, were you assuming that they were all from dark matter? And that's how you
Yes.
set the limit?
Yeah.
So how confident can you be?
Well, I mean, that's the question is the same, for example, when they set limits on CMB, from CMB anisotropies on the dark matter annihilation cross-section. And then you can set limits on N effective, and then you can set limits on whatever processes. So the rule is you take one tooth fairy. Sorry?
So these would be the strongest limits you could ever hope to get.
Exactly, yeah.
But they might be much bigger because it could
Yes.
be some similars.
Essentially.
Yes.
Any other questions? All right.
All right. Okay.
Thanks again.
Can you leave the rest of the space for 1 minute?
Oh, sure.
I slept this morning and then fell down this
I feel like I'm not invited.
Sorry,
I had to run out.
Not
My
easy stairs.
No,
son's school
that's
card.
fine.
So.
Stairs, not
Yeah,
easy.
but no, it's and I have new shoes. So, but anyway, other than
I think
that,
you're the program coordinator for Mark and Cosmos.
You guys want to fight it out? You don't want me to see
Yeah.
dirty fighting.
Because you told me as a problem.
Oh, okay. Oh, wonderful.
Yeah.
Which is
Okay.
You didn't put the names together.
Yeah, the first paper I discovered.
I still wouldn't mind joining just to say hi,
Yeah.
and then I can play with my phone. What did you want to ask me?
I mean, ultimately,
What was the-
Because he was on
really
the
the semester. That's what I meant.
Yes.
Okay.
Do
you wanna ask me
the
about-
raw signal to what you maybe could expect. Yeah, just comes from
One dictator, just
What was your status?
Yeah.
You got to run. The non-cluster? Oh, okay.
through the built-in analysis.
Yes.
show returns.
Right, right.
I see.
I haven't tried to troubleshoot that.
Zero. Okay.
I see. Just like a built-in
Okay. They didn't
So there's like a whole
mark-out chain thing.
There's like a
They
whole
went to the system.
it'll run the
How long have you been in Mars?
It's my second.
Okay.
all year, and that's not formal.
And you, this is your first.
I see that doesn't work.
That's my second
But the markup change?
Where did you do your markup?
I was at the IIS.
Oh,
Okay, so the problem might be just in the analysis.
Started late
I
and
mean,
we finished early.
most
Oh,
of
you
the
finished?
postdocs and
I see.